kilonewton meters, right? And now I need the resultant of the distributed torque, which should be this torque per length times the length. And the length that I'm interested in is this length right here. Okay? And what is that length? It's x2 minus 0.8, right? Yeah. x2 minus 0.8 meters. And so then my torque is minus 2 kilonewton meter per meter times x2 minus 0.8 meters. And this all equals 0. Okay. So that is my function. And then TBA is, if I would have to move everything to the other side, it would be like 2 kilonewton meter. I'm going to let that meter per meter cancel out. It would be 2 kilonewton meter per meter times x2. Let's see, plus here 1.6 minus 1.6. Yeah. Is that right? If I do negative, okay, I'm just going to do some math here. 2x2 minus 1.6 kilonewton meters minus 1.2 kilonewton meters. And then here, then if I just simplify this one more time, I get 2 kilonewton times x2 minus 2.8 kilonewton meters. Okay? Alright, so that's my internal torque function from B to C. So what's even more important now, we define the origin here. The boundaries for x2, we can only apply between discontinuity and discontinuity, right? From B to A for cut 2. So that means x2, what are the bounds for x2? Can I go from 0 to 2.3 or 1.5? What are the bounds for x2? Is it from 0 to 1.5? So would you be able to do from 0 to the cut? I agree. It's right. Well, there's a 0 to the cut, right? There's a cut here, but you know this cut is between discontinuities, right? So this x2 is defined for anywhere from B to C. Or I'm sorry, not B to C, from B to A. Okay. So there's this cut here, and it's defined anywhere from B to A. Okay. All right. So what are the bounds for x2? What are the numerical bounds? It can't be. What's the lowest number it could be? x2. The lowest number can be between B and A. Yes. Okay. So what would be the bounds of point? So like when x2. Okay. Here. Sorry. Maybe I'm asking the right way. When I'm at point B, what's the value of x2? Yeah, 0.8. Okay, good. All right, 0.8 meters. And then when I'm way over here at A, what is the value of x2? What is the value? 0.8 plus 1.5, so 200. 2.3. And this is going to be important when we calculate the angle twist. Okay, here's why. All right, so here, I have in segment CB, do I have a concentrated torque or is it a function of x? CB. In the first segment right here, in the first cut. Do I have a concentrated torque or is it a function of x? A concentrated torque. So that means I can actually say this is TCB LCB over GJCB. Okay? How about in the cut 2, do I have a concentrated torque or a distributed torque? Distributed. So that means I'm going to have to integrate for the angle of twist. And that's going to be some bounds. It would be TBA, which is a function of x2, times, I'll just put parentheses x2, dx2 over GJ AB. And thankfully it's constant, so GJ is constant for the whole shaft, so no big deal. But one of the things that's important is like what the heck are the bounds for this integral, right? And that is from discontinuity to discontinuity. So here it would be from 0.8 to 2.3 meters. Okay. Yep. And now we solve and we plug and chug. And so, all right. So here, when I want to calculate the angle of twist, what is this? 1, 2, 3. This angle of twist here, right? Then I would have, I'm just going to pull out here. And then this would be TCB was negative 1.2 kilonewton meters times the length of CB, which was 0.8 meters. Plus, let's factor out the GJ, so it's from the integral from 0.8 meters to 2.3 meters times TBA, which is 2 kilonewtons, x2 minus 2.8 kilonewton meters, dx2. And then I integrate. You don't want to mess up the GJ calculation. There is also this. You have to also recognize that this 1 over GJ. The G was 38 gigapascal, so that's 38 kilonewtons per millimeter squared. J is pi over 2 times the radius, so the diameter was 80, so here this is 40 millimeters to the fourth. This is in units of kilonewton. I'm going to get units of kilonewton millimeter squared here. This is going to be kilonewton millimeter squared. Okay. The top, this numerator, all this stuff, and all this business can give me kilonewton meter squared. Do you see that? Okay. This is kilonewton meter squared. So you have to do some conversion. You have to either convert the millimeter squared down here to meters, or the meter squared to millimeters. So I think what I would do is convert the meters to millimeters. So I would probably put 1,000 millimeters divided by 1 meter quantity squared to convert everything in the numerator, and then I would evaluate, all this stuff. This would be the same thing as that's right up here. Yeah. Okay, and I would get an angle of twist, and that angle of twist result would be in radians. And let's see, I think I got negative 0.00334 radians. Negative 0.00334 radians. Okay. Okay. All right. Now, okay. So you feel good? Yeah, I feel good. Okay. Do you want to calculate the shear stress, or are you all right? Shear stress. The maximum shear stress. That's fine. Good. Okay. All right. Yeah, having the internal torque diagram is useful. Internal torque diagram. Okay. Internal torque diagram. But it's not even okay. Let's just take care of it real fast. Okay. So here, if I want to calculate, so now I'm going to try to calculate the absolute maximum shear stress, okay, due to this torque. So I found already previously here I have this distributed torque, 2 kilonewton meter per meter, and I have this 1.2 kilonewton meter like this, okay? And I found, this is like a shear diagram, really, and I draw vertical lines at discontinuities. I even told you that this is 1.8 kilonewton meters like this, but it's all good right here. And here, if this is my internal torque diagram, we knew in the segment here that I had a constant internal torque of negative 1.2 kilonewtons, like right here, in the segment CV, negative 1.2, and then I had this function, okay? And so here, so this was CBA, and CV I had negative 1.2. This was in units of kilonewton meters. Okay. And then if I looked at my equation right here for the internal torque of BA, I knew it was a linear function, so I know it's just going to be a line. And it has a positive slope, so it means it's increasing, right? And it's really increasing at a rate of 2 kilonewton per meter. So what it's saying is I have a positive slope, it's going to be increasing. Really the area here would actually be how much I change. It's going to be 3. But anyway, so this would be but what I would get is a positive 1.8 kilonewton meter here at the end. Okay. So here, so when I put x equals 0.8 here, I should get negative 1.2 from this equation. And then when I put x equals 2.3, I should get positive 1.8. So 2 times 2.3 is 4.6. Minus 2.8 is 1.8. So that's my torque diagram. And my maximum internal torque is the 1.8. So T max is 1.8 kilonewton meters. So that means my maximum stress is happening right here at the support, inside at the support. Okay. And so now I would just say the shear stress tau is this T rho over J. Okay. And here, my cross section is a solid circular shaft. So when I look at my cross section, like this. Here's the center. My maximum, like if I asked you for the shear stress distribution, right here, okay, on this, let's say this radial line right here, okay, where would my shear stress be maximum? For this distance. For this distance, good, right here, okay. And I have a positive internal torque, so is my torque going counterclockwise or clockwise? Is it going into the page, or is it coming out of the page? Into. It's technically out of, because I have a positive internal torque here, and a positive internal torque, it comes out of the cut, right? So really, this torque is going like this, 1.8 kilonewton meters. Okay, so this is a positive internal torque. I curl my fingers in a direction, and then my thumb will be pointing out of the page here, right? And you said it's maximum here. The distribution shape is a linear, constant, parabolic. It's linear, and what's the value right here at the middle? Zero, good. So here. Well, maybe parabolic. It wouldn't. Oh, our shear stress to transfer shear is parabolic. Oh, yeah. If you have like a hook, anyway, that's what we're not good at. Okay. And so this is where my tau max is happening. I know that the 1.8 kilonewton meters is acting this way. That's why I drew the arrows going this way, just like like I said, we're smearing a whole cheese. You know what I'm saying? And here I want to solve for a number here, this tau max number. I just take all the information you told me. This is 1.8 kilonewton meters. I probably want to convert it into millimeters, so I'll do 1,000 millimeters per meter. The radius, the outer radius is 30 millimeters. We're given a diameter of 80, okay? Divided by the polar moment of inertia, which is pi over 2 times the outer radius to the fourth. And if I calculate this, I would get units of millimeter squared, which is 1, 2, 3. I think it's 0.0179 kilonewtons per millimeter squared, which is a gigapascal. And this would be 17.9 newtons per millimeter squared, which is a megapascal. 17.9 megapascals, and this would be equal to 17.9 MPa. Right. And that's that one. All right. Switch over. Welcome to Office Hours, and today we are talking about shear flow. We're going to do a shear flow example, and let's see, in this problem we are given a beam is constructed. It's got 2 boards, like 2 2x4s, nailed together, and with 2 rows of nails. That's kind of important, of nails at 6-inch spacing, and let's see, and we know that there's like a face of a cut from a shear diagram. The shear force that's applied on the cross section due to transverse shear is 600 pounds. Right here, and we would like to find the force applied or resisted by each nail. One board, here's the other board, and then there are nails that go through like this, and they continue, and they have a spacing of 6 inches. All right, and there's another set of nails, like over here, which also has a spacing of 6 inches. Okay, and so all the nails have an area of responsibility of about 6 inches. So, like for instance, if we take this middle segment of nails, this area of responsibility is halfway to each set of nails. So it's responsible for this area right there. And this area has a total length of 6 inches. Yes, and a width of 6 inches. Oh, that's interesting. Okay, all right. Oh, it's a terrible drawing. This should have been like this, and this should have been like this, huh? Or like that, yeah. Okay, all right. And we know that the shear force, the transverse shear here, this V is 600 pounds. Okay, and so what we're looking for is the force applied on each nail, 2, and the force applied. When we learned in class, this force applied on the nail is the shear flow times the spacing divided by the number of shear planes. Alright, okay. And this shear flow is VQ over I times S divided by the number of planes. Number of shear planes. Okay? Alright. Okay, let's see here. So let's start with the simple stuff. Do I know the shear force?
Yes.
Yes, I know the transverse. I know the shear, so check. Do I know moment of inertia?
Not yet.
Not yet, that's right, not yet. And here, so let's see, let's get some geometric properties. So 3, the MOI, and here, you know, the nails are holding both boards together, so both the boards together, both the 2x4s can act like a single beam. So that means we get to use one big old moment of inertia, and it's just a rectangular cross-section, so I is 1/12 the base, 6 inches times a height of 4 inches, cubed, and this was 6 inches of each of these. It's 2 inches. Alright, and what is that? What's that moment?
32 inches to the floor.
32 inches to the floor. Yep, that's right. And so we know the moment of inertia. I check. We do know the spacing. Yeah, the space that's required to cover, right? The spacing, so it's 6 inches, right? So this is 6 inches, all right? And then now the first moment of area and the number of shear planes are related. Yeah. So let's see, what area should we use for the first moment of area, especially when it comes to shear flow and nails or connectors?
We should use the top section.
I agree. We should use the top section. And how would we define the top section from where to where? Like from here to here?
Well, the neutral axis is the center, so.
It's the center. Now we choose this location. I think we should choose this location not because it is the neutral axis, because that's where the two boards are connected. The nails are intended to hold these two boards together, and the point that's important is where they're in contact, which happens to be, in this case, at the neutral axis. That's where the nails have to go across to keep these two boards together. Okay, so that's where if I cut it, I'm disconnecting the two elements, right? If I cut it there, I'm disconnecting the two elements that the nails are holding together.
Yeah.
Okay, and so that's what I want to cut for the first moment of area. And so now I can choose either the top or the bottom. Let's choose the top, maybe here. And this would represent A prime. Okay, this Q, this first moment of area Q, which is the sum of A prime times Y bar prime. This is going to be that area. There's only one of them, so that's 6 inches times 2 inches. And Y bar prime is the distance from the neutral axis to the center of the element, which in this case would be 1 inch. Times 1 inch. And this is 12 inches cubed. All right. And so this is 12 inches cubed. And so how many shear planes are there?
1.
Okay, so technically there's only one shear plane. Okay, all right, so this is one shear plane. All right, one plane, okay. All right, and so now I'm going to calculate the force that's applied on the nails. So the force that's applied on the nails, I'm going to solve it. Right here, it's going to be V is 600 pounds times Q, which is 12 inches cubed, divided by 32 inches to the floor, times 6 inches. Yeah, come on in. 6 inches divided by 1 shear plane. And so this is, what is the force here?
I got 1350.
1350 pounds. Yeah, why not? I don't know. Yeah, I think that looks right.
Okay.
Yeah? Yeah, like that's 7,200 divided by 32 times 6. That's right. All right. I don't know. I'm tired, man. I just want my gas good.
Oh, yeah.
All right. 1350 pounds. I'm going to tell you right now, this is not the right answer to this problem, though. Oh. Because it's asking for the force on each nail. And how many nails are going through the shear plane?
6.
Well, at least in terms of this orange area that we looked at, how many nails are holding that board together there?
2.
2. So, what is the force applied on each nail is what?
1350 divided by 2.
Yeah, that's it, man. That's it. It's just it's half that each nail. If it was just one nail in here, we would say it's got to take all the 1350 pounds, right?
Yeah.
But there's 2 nails in that same location, so we can break it up. We'll say they take an equal role in holding down the zone.
Yeah.
And so it would just be 1350 divided by 2, which is that 675?
Yeah, that's right.
Yeah, 675 pounds. So each nail is taking up 675 pounds. Another way to look at it is, you make this cut here, but you end up cutting through 2 nails, so it's kind of like 2 shear planes. That's another way to look at it. You don't have to. You don't have to, but that's what's going on. And then we could, using this now, the model of the nail is really just here. The force applied on the nail is 675 pounds, and then this would be a case of direct shear, and there would be a shear here. And if I asked you for the average shear stress in the nail, then you could, right, in the nail itself, yeah,
you would use equilibrium to solve it.
right, to get V nail, and that would tell you from equilibrium V nail would be 675 pounds, and the average shear stress in the nail would be this V over the area of the nail. This would be a case of direct shear, and this would be 675 pounds divided by whatever the diameter, pi over 2 4 d squared, 4d squared for the area of the nail. We gotta be careful keeping these pi over 4, pi over 2 straight, because like we got like polar moment of inertia of a circle, area moment of inertia of a circle, and area of a circle. Yeah. So when in doubt, just go back to pi r squared. Yeah. Okay. Yeah. And then and think from there. All right. Well, that's this problem. See ya. Alright, what's up everyone, welcome back to Structure Free Office Hours, and in this video we are meeting to do an example problem with biaxial bending or an unsymmetric bending problem. And here, the unsymmetric bending equation, it really, because you're bending about two axes on the cross section, this normal stress is negative mzy over iz plus my, a distance z over iy, right here. And so you can tell already we're going to have to calculate moments of inertia about the z and the y axes of the cross section, as well as, even before that, determine the neutral axis location, or at least the centroid, the geometric centroid. And here I have this key shape. I know that I have one line of symmetry up and down the middle, and my centroid will lie somewhere here. And so I want to find this distance. I want to find the distance to the neutral axis, OE. It's all good. Right here, this will be my neutral axis. So one of the first things I want to do is, I'll just go ahead and look at the geometric properties. But I have this cross section. I have a 2 centimeter moment that's actually pointing like this. It's like this. There's my angle. 60 degrees. So here, the moment is actually here on the face of the cross section, like this, right here. And so I put my thumb in a double-headed arrow direction. This upward direction will represent plus y, and this direction will be plus z, and coming out of the page will be the x-axis, and this is the moment that's being applied on the cross-section. So one thing I want to do is find the centroid, this location here in particular. I would like this distance from, let's say, either the bottom or the top. I'll choose my bottom as a reference, so I'll call that y bar. Alright, so one of the first things we're going to do is determine some geometric properties. Alright, so for this, I already know, at least I know where it is in terms of left to right, but up and down, I'm trying to find y bar. Y bar is the sum of ai, yi over the sum of a, the first moment of area. And here I would break this up into two elements. I might call this one element 1, and I'll call this one element 2. And now I'm just going to follow this pattern of base times height, so 200 times 50. Yi is the distance from the reference, which is down here, this is my reference, to the center of the element, which would be right here. Here's the center of the element, so that is 200 plus 25, so it's 225 millimeters, plus the area of the other element, area 2, which is base times height, 50 times 200, and the center of this element from the reference is 100 millimeters, divided by the total area, so that's 200 times 50 plus 50 times 200, and then when I calculate this out, I'm trying to tell me that I have 162.5 millimeters. Yay. Alright, that seems reasonable. Yeah? That seems reasonable. Okay, so 162.5 millimeters. So I have that. Now I want to, because I know at least in this relationship I have to determine IZ and IY, right? IZ and IY. And so here, as part of my geometric properties again, I want to calculate my moments of inertia about the z-axis. So with respect to the z-axis, that would be as if I'm resisting rotation about the z, right here. So this is what we've calculated in the past with just our my over I formula. This is the bending that we're used to. Okay, and so here Iz is the sum of IZI plus AI dyi squared. And it's dy because the distances are in the y direction, right? The distance from the neutral axis to the center of each element. And so here, this would be, so for instance, area 1, I'm taking moments of inertia about its horizontal axis. So that would be 1/12 times 200 times 50 cubed, plus the area of that, which is 200 times 50. And then dy is really the distance from, dy is the distance from the center here to this right here. So this would be dy1, the center of the element, the distance from to the center of the element from the neutral axis, which really, if it's just 225 minus 162.5. And we want to make sure that we remember to square that quantity right here. Then the second element would be plus 1/12, the base, which is 50, times 200 cubed, plus 50 times 200, and then the distance from the reference, I'm sorry, from the center, distance to the center of element 2 from the neutral axis is just 100 minus 162.5. And again, and now if I go through and I calculate some numbers, IZ, it would be, what would it be? Let's do some calculations. 2.083 times 10 to the 6 plus that's a total. There you go. Okay. Let me pause this.
But I got 11 million.
11. Oh, okay, yeah. So I got 113.54 times 10 to the 6. So maybe we're off by a factor. Okay.
113.54 times 10 to the 6. Yeah.
Millimeters to the 4th. So that's moments of inertia about the z. Right here, that's the moment of inertia about the z. Now I want to find the moment of inertia about the y-axis. Okay. So about the y-axis, another one way to look at this is as if I turn this thing to the side. I think for some students this is easier to see. Like if I turn it to the side and I go like this, and then the y-axis would be this thing right here.